Hello and welcome back. Hey, I'm down here. I had to move my head out of the way because I was blocking some parts of the slides. Let me know if you like this new position, by the way. In this video, we're going to look at finding the slopes of tangent lines of polar curves. So to find the slope of a polar equation, r equals f of theta, in other words, where we have r solved for as a function of theta, turns out we can use parametric equations. We know that x equals r cosine theta. That's one of the equations that relates polar coordinates to Cartesian coordinates. And here, if r is a function of theta, we could replace r with f of theta. So now we have x all in terms of theta. Theta is going to be our new parameter. It's like our new t, right? Theta is like t was before. Similarly, y equals r sine theta, so we can replace r with f of theta. So we get y equals f of theta times sine theta. So again, the parameter here is theta. Now, we learned before that if we want to take the derivative, if we want to find the derivative of y with respect to x, in other words, the slope of the tangent line when we have parametric equations, then we'll do y of t, dy dt over dx dt. But again, instead of t here, we have a parameter theta. So for polar equations, it'll be dy d theta over dx d theta. Now we know what y and x are in terms of theta. So like, y was r sine theta and x was r cosine theta. Here I'm just writing r instead of writing f of theta. But remember that r is some kind of function of theta here. Well, to take the derivative on the top, we would use the product rule, right? If we have a function of theta times a function of theta, well, we're going to go ahead and use the product rule. First times derivative of second plus the derivative of the first times the second. When you do that, you end up with something like this. And here I kind of switched the order around a little bit just to follow the way that the book wrote the formula. Here we did derivative of r with respect to theta, leaving the sign alone, and then plus r times the derivative of sine theta. Same kind of thing on the bottom. So this would be a formula for finding dy d theta if you know r is a function of theta. Now, some people just try to memorize this formula, but I like to rederive it, just always use the product rule. It's good practice for the product rule. It's been a while, since we've had to do a lot of product rules. And also then you don't have to memorize a new formula. You just kind of do it. You don't have to memorize it. All you have to remember is how to find dy dx using parametric equations. So for example, what is the slope of r equals 2 plus 3 sine theta? This is example 6, that was that polar equation, at theta equals pi over 2. Well, we have x equals r cosine theta, so replace the r with, in this case, 2 plus 3 sine theta, and then we have cosine theta. Using the product rule, we can get the derivative of x with respect to theta. So that's going to be the first times derivative of second plus the derivative of the first times the second. Then we can start simplifying a little bit. We've got negative 2 sine theta minus 3 sine squared theta plus 3 cosine squared theta. So there's dx d theta. Y equals r sine theta, so that's 2 plus 3 sine theta all times sine theta. And again, use the product rule to find the derivative of y with respect to theta. So first times derivative of second plus second times derivative of first, or plus derivative of first times second. And then we can simplify, and we end up getting something like 2 cosine theta plus 6 sine theta cosine theta. Now we just divide the two. Take dy d theta divided by dx d theta, and that's going to be an expression in terms of theta that will give you the slope of the tangent line. It'll give you dy dx, the slope of the tangent line. So if we're interested in theta equals pi over 2, we can plug in pi over 2 into that equation that we got, or that expression that we got. Evaluate all these things, and then we get 0 over negative 5, which is 0. So the slope of the tangent line at theta is pi over 2 is 0. Let's check back to figure 13 where we had actually drawn example 6. If we look at theta equals pi over 2, we can see that the tangent line there is going to be a horizontal tangent line because it's right at the top of the figure, and that's going to be a horizontal tangent line, which has slope 0. So that checks out. So notice that we're going to get horizontal tangent lines whenever dy dx is equal to 0, which is going to be when the top of the fraction is 0 and the bottom is not 0. In other words, when dy d theta is 0 and dx d theta is not equal to 0. That was the example that we just looked at. The top is 0, the bottom is not 0. In other words, dy d theta is 0, but dx d theta is not equal to 0. We're going to get vertical tangent lines when the bottom is 0 and the top is not 0. So when dx d theta is 0 and dy d theta is not equal to 0. And if both the top and the bottom are equal to 0 at that theta value, so if both dx d theta, let me move my head again. Whoops. It still blocks it no matter what. If both dx d theta is equal to 0 and dy d theta are equal to 0, then you might have to check the limit as theta approaches that theta value where that's happening of dy over dx, and possibly use L'Hopital's rule here because you're going to get a 0 over 0 case, or possibly try to cancel factors and simplify. Most likely it's going to involve L'Hopital though. We'll handle example 7 in the next video. Thanks for watching, and see you then.